Okay, so a symmetric matrix. Symmetric matrices, well, first of all, what is a symmetric matrix? A symmetric matrix is a matrix such that the transpose of the matrix equals itself. A transpose equals A. And such a matrix would have to be a square matrix. Okay, and the main diagonal entries are arbitrary, but the other entries occur in pairs on opposite sides of the main diagonal. So here, for instance, you see three symmetric matrices in this example one. Okay, well, of the following matrices, only the first three are symmetric. So take a look at them. I mean, if we look, for instance, at the second matrix here, you see how you got a diagonal. It's a 3 by 3, and you have a -1 across from a -1 along the diagonal. It's like, think of that diagonal as a mirror. The 8 is reflected across the diagonal. This 0 here is reflected across the diagonal. Okay, so it is a symmetric matrix. It is a symmetric matrix. For the third matrix, okay, you have a B here, and it's reflected across the diagonal. C is reflected across the diagonal, and E is reflected across the diagonal. Whoops, hold on. Don't want to have that much highlighted. Okay. And then here you have the zeros reflected across the diagonal. Hold on. You have zeros reflected across the diagonal. So those are examples of symmetric matrices, and they occur a lot in applications. Like, for instance, in statistics, I don't know if you've heard of like a variance covariance matrix. That would be something maybe not all of you have heard, but basically it's a matrix that gives the statistical relationships between variables, and those matrices are symmetric. Symmetric matrices are very important in applications. You know, below the symmetric matrices in example one, they have non-symmetric matrices. So based on that example, do you see the difference? Do you see the difference between symmetric and non-symmetric matrices? Are there any questions? Let me ask you this: for the non-symmetric matrix, the third one, this third matrix here, why is that not symmetric? Just kind of unhighlight some of this other stuff here. I mean, we should be able to identify why matrices aren't symmetric as well, right? One moment, let me get some of this yellow off. What's going on with that third matrix? Okay, very good, Eleni. The third non-symmetric matrix is not square. It's a 3 by 4 matrix, 3 rows, 4 columns. So that matrix is not going to be, a symmetric matrix. Okay, and hold on here. Now, where am I at here? Uh-oh, I'm in the wrong thing. Wait. Hold on. Let me bring it back. Hold on, everybody. Let me bring it back. Right. Okay. What about the second matrix, or the first matrix, the first non-symmetric matrix? This matrix here. Why is that matrix not symmetric? What's the problem there? Why is the first non-symmetric matrix, why is that non-symmetric? What's the reason why? Who thinks they can tell me? Let's see. Eleanor says the numbers in the rows and columns aren't the same as the. Okay, so that's right. So the 3 and the -3, right? The first row, second column, the number is -3, but the first row, second column, you have a -3, but the second row, first column, you have a +3. So that ruins it. Similarly, for the next matrix here, okay, you have a -6 and a -4 across the diagonal. Is this acting up again? What is going on here? Hold on. Now, where is this thing? Hold on now. Hold on. Better. Right. So the -4, -6 across the diagonal don't match in the second matrix, second non-symmetric matrix. So are there any questions regarding symmetric, distinguishing between symmetric and non-symmetric matrices? Are there any questions at all? Okay. All right. Very good. Very good. Well, let's go ahead and proceed on. So why, so these matrices that are symmetric, I mean, how many think symmetric matrices are kind of beautiful when you look at symmetric matrices? They look kind of beautiful. They look kind of interesting, don't they? Yeah, Eleanor likes them. Sure. And they have some really nice properties. They have some really, really nice properties. So I want to bring up an example here. Okay. And this is the example. And I want to give you a moment to copy down the example, okay? Note that A is a symmetric matrix. A is a symmetric matrix. Okay, so copy down the example. Okay, so in this example, you're being told what the eigenvalues and eigenvectors of this 3 by 3 symmetric matrix A, where you're being told what they are. And, you know, of course, if you were to use a like MATLAB to get the eigenvalues and eigenvectors, we know that the eigenvectors sometimes aren't going to be nice looking. So obviously you can scale the eigenvectors appropriately and to get you 3 nice ones. Now, well, I want to say it's the right way. The matrix A. Can the matrix A be expressed as P times D times P inverse? In other words, if you think back to, let me find the right section here. If you think back to section 5.3, we called this diagonalization, right? When we said that a matrix A, if a matrix A is similar to a diagonal matrix, that means A equals P times D times P inverse. We say that the matrix A is diagonalizable. So would this matrix A, you know, be diagonalizable? Can the matrix A be written as P times D times P inverse? Benjamin says yes. Why is that? Why do we know that for sure, Benjamin? How do we know that for sure? Good. Good, that's right. The eigenvectors form a basis. So we have the eigenvectors are in 3-dimensional space, and you have 3 linearly independent eigenvectors. Okay, now I guess we didn't show that, but we could show that. These 3 eigenvectors are linearly independent, and so A will equal P times D times P inverse. Okay, but what we're asking now is something a little different. We want to find a matrix P and a matrix D such that the matrix A equals P times D times P transpose. Okay, so I mean, let me ask you this. Why can't we just, I mean, why shouldn't we just be happy that the matrix A can be expressed as P times D times P inverse? And then, you know, that would help us find things like, you know, A to the 4th power. We can find powers of a matrix, and it's just nice to be able to do that. But why would it be kind of better to write the matrix as P times D times P transpose when you compare these 2 factorizations of the matrix A? What makes this second factorization a little nicer than the first factorization? That's exactly right. That's exactly right, Benjamin. The transpose is easier to find than the inverse. Okay, to find an inverse of a matrix takes effort. It takes effort, it takes computing power, it takes effort. So certainly, if we can express this symmetric matrix A as P times D times P transpose, that would be nice. Okay, so Are there any questions before we move forward here? Okay, let's go ahead and move forward then. So in our solution here, you know, what would the matrix P, I want to be a little careful here now, hold on. Yeah, in the matrix P consists of those eigenvectors. The columns of the matrix P are the eigenvectors of the matrix A. And interestingly enough, these three vectors are orthogonal. Okay, kind of interesting. You know, hey, they happen to be orthogonal. The diagonal matrix is here, and you could show, I did it in MATLAB, you could verify that the matrix A does equal P times D times P inverse. However, the matrix A will not equal P times D times P transpose for this particular P matrix. Okay, it will not equal P times D times P transpose. So what can we do? Well, you know, interestingly enough, for this symmetric matrix, the eigenvectors for the different eigenspaces, remember there are three separate eigenspaces, one for each eigenvalue in this case, because we have three eigenvalues. It turns out when you have a symmetric matrix, any two eigenvectors from different eigenspaces will be orthogonal. So this is no accident that these eigenvectors are orthogonal. But what we're going to do is we're going to define another matrix P. Here, I'll circle it in red, given by this matrix. So remember, eigenvectors, if you have an eigenvector, any multiple of an eigenvector is also an eigenvector. So what did I do? Like for instance, the first eigenvector here, the eigenvector v1, which is -1, 1, 0. Well, okay, that eigenvector now, I have a new eigenvector, -1/√2, -1/√2, and 0. What did I do? What did I do to this vector v1? How did I get this matrix here? Or that vector, I should say. Oh, yes. Good catch. Thank you, Lewis. This should be, this term here, this should be positive. So please make sure that this term is positive. Absolutely. Thank you. Good catch. Let me fix that on my notes as well. I mean, look at your eigenvectors here in this matrix P above, and look at the vectors in this other matrix P. What am I doing to the eigenvectors? What am I doing to the eigenvectors to get this matrix P here? Hold on here. That's right, Lewis. I'm normalizing them. And the columns are orthonormal, right? So these columns here, maybe I'll put this in blue. the columns are orthonormal. And the columns are orthonormal because they are orthogonal and they all have length 1. The matrix T will let as is. So in this situation, and I checked it in MATLAB just because I wanted to do it, I knew it was true, but this matrix A will equal P times D times P transpose for this P, right? This P here. So that means then really that P transpose would be equal to P inverse, right? It has to be, right? Because A does equal P times D times P inverse. So P transpose would have to be equal to P inverse. Why is this true in this second case? In this second case, the matrix P is an orthogonal matrix. An orthogonal matrix has columns that are orthonormal. And so P inverse equals P transpose. How many remember orthogonal matrices? Recall that. Okay, good. Good, Eleanor. Excellent. So when this happens, we say that the matrix A is orthogonally diagonalizable. Okay, that's what we say the matrix A is, because A equals P times D times P transpose. So this is really nice. If a matrix A is orthogonally diagonalizable, then that's very a very convenient factorization to get for a matrix. Okay, but we have to ask ourselves then, under what conditions would a matrix A be orthogonally diagonalizable? What do you think? What kind of matrices do you think are orthogonally diagonalizable? I'll give you a hint. Hold on here. Hope I got this right. Okay. Starts with an S. Okay, this is like Wheel of Fortune. How many have seen Wheel of Fortune? All right. Put a Y in here. Okay. Good, good. All right, Ben, good. Symmetric. So it turns out that symmetric matrices, man, I got my little things. Symmetric matrices are going to be orthogonally diagonalizable. And that's going to be true in general. I mean, in other words, if you have a symmetric matrix, say, it's guaranteed that you can orthogonally diagonalize it. And what I'd like to do is I'd like to look at a few of the little proofs in the book to sort of help you, you know, feel comfortable with this. And then we'll go ahead and look at another example. But are there any questions? All right. Maybe give me a thumbs up if you're comfortable and you know, have this copied down. We'll move on to the book. Okay, maybe just a few thumbs up when you're ready. Okay, very good. Ben's good. Andres is good. Good. All right, and maybe one more person, and then we'll get going. Okay, thank you, Abby. Thank you, Eleanor. All right, all right. So let's take a look here in the book. Let's take a look at the book here. Okay, and let me just go down here to whoops. This theorem 1. This theorem 1 says that any two eigenvectors from different eigenspaces are going to be orthogonal. Okay, and of course that means linearly independent, right? So if you have a symmetric matrix, any two eigenvectors from different eigenspaces are orthogonal. And we saw that in the little example that we just looked at. Let's prove this. Let's prove this. So go to the next page. Here's what they do. Let V1 and V2 be eigenvectors that correspond to two distinct eigenvalues, say lambda 1 and lambda 2. And to show that the dot product of those vectors equals 0, and we want to show that because that would show that the two vectors are orthogonal. Well, what they choose to do, and you know, this is just kind of a proof somebody made up. They're going to take lambda 1 times the dot product of V1 and V2. Now, lambda 1 V1 dotted with V2 would be equivalent to lambda 1 V1 transpose times the vector V2. But lambda 1 times V1, since V is an eigenvector, don't forget, V is an eigenvector, so lambda 1 times V1 can just be written as A times V1. All right. Now, let me know if you have any questions. So far, so good? All right. Well, so we have a matrix product, A times V1. I mean, V1 is it's a vector, but it is a matrix too. The transpose of a product is the product of the transposes in reverse order. Okay. And so now you can write, well, and A transpose is equal to A because A is symmetric. So you can rewrite this V1 transpose A transpose times V2 as V1 transpose times A times V2 because A is symmetric. A transpose equals A. But now, remember, V2 is an eigenvector. So A times V2 is just lambda 2 times V2. And so now what they do is they say, okay, well, let's bring the scalar out, bring that lambda 2 eigenvalue out. And so lambda 1 V1 dot V2 will equal lambda 2 V1 dot V1. So far, so good? All right, good, good. Well, and now what they do, I might, very good, very good. Thank you, everyone. Let me maybe go to the whiteboard here for a moment because I want to fill in this this step here. Okay. On the whiteboard, and maybe I'll use my stylus here. So we have lambda 1. Hold on here. Yeah. Lambda 1. Hold on. Let's try it again. You have lambda 1 times V1 dotted with V2 equals lambda 2 times V1 dotted with V2. And by hypothesis, lambda 1 is not equal to lambda 2 because we're assuming that they are distinct eigenvalues. So what we can do here is we can subtract from the right side the lambda 2 V1 dot V2. I could subtract that. And of course, it's equal to then 0. It's not a 0 vector on the right side. It's just a 0. It's a scalar. And then looks here like I have a common factor, V1 dot V2. So I can factor that. Okay, and write, you know, I mean, I get to here. Now, you know, you have here, I mean, what you have here, you have a scalar, and you have another scalar. The dot product of two vectors is scalar. You have a product of two scalars being equal to 0. So this is like, you know, if you had A times B equals 0, if A times B equals 0, then that means what? A equals something or B equals something. What do we put there? If a product A times B equals 0, then either A equals blank or B equals blank. What are we going to put there? What? Zero. That's right, Haley. Okay, so either, well, hold on. Let me just, okay, so either A equals 0 or B equals 0, one or the other. So this implies that lambda 1 minus lambda 2 equals 0, or the dot product of V1 and V2 equals 0. And of course, if lambda 1 minus lambda 2 equals 0, that means lambda 1 would have to equal lambda 2, right? Oh, but this can't happen. That can't happen. I can't have lambda 1 equal to lambda 2. That's not a possibility. This can't happen. Why? Why can't lambda 1 equal lambda 2? Why is that not allowed? That's right. That's right, Benjamin. We originally said that they were not equal to each other, that lambda 1 and lambda 2 were distinct eigenvalues. And the eigenvectors V1 and V2 were corresponding eigenvectors. Well, V1 was an eigenvector corresponding to lambda 1, and V2 was an eigenvector corresponding to lambda 2. And for this symmetric matrix A. So it turns out that because of this here, this in our hypothesis, the only option we have is that the dot product of V1 and V2 equals 0, and that means that V1 is orthogonal, it's perpendicular to V2. And that proves the little theorem. And this shows that any two vectors from different eigenspaces for a symmetric matrix, any two vectors from different eigenspaces will be orthogonal. Okay. Are there any questions on that? All right, let me go back to the book then. So this then finishes out the proof, right? That finishes out our proof. Not a hard proof, right? But it was in the proof, we relied on the fact that A was symmetric, right? We could have gotten where we got without A being symmetric. But it's just really cool to see how your, your algebra knowledge comes into play as well. So this special type of diagonalization is crucial for the theory of symmetric matrices. And like I emphasized, a square matrix A is orthogonally diagonalizable if there's an orthogonal matrix P and a diagonal matrix D such that A equals P times D times P transpose, which equals P times D times P inverse. But that means the matrix P has to have orthonormal columns. Okay, so such a diagonalization requires n linearly independent and orthonormal eigenvectors. But when is this possible? We've seen this occur for symmetric matrices. Well, if A is orthogonally diagonalizable, if that's the case, then it turns out that A transpose will equal A. It follows that A transpose equals A. I mean, take a look at that. You take the transpose of P times D times P transpose. That means, if A is orthogonally diagonalizable, it equals P times D times P transpose. And then the transpose of that matrix product is the product of the transposes in reverse order, and you will get you'll get back the matrix A, and therefore A is symmetric. Okay, and we can show the converse is harder to prove, but the point is every matrix A is orthogonally diagonalizable if and only if A is a symmetric matrix. Okay, are there any questions on that? Okay, how many think this is pretty cool? Just check one thing here while you're thinking on it. One moment. What I'm doing here, I'm trying to, symmetric matrices are found in statistics a lot. But I'm just, going on the web, and they comment about control theory, which of course I'm not an expert on control theory, but symmetric matrices come up in other fields. They come up in other fields. And I was just looking to see some other applications here. Let me just see here. Well, actually, you're going to see some next week, right? We're going to talk about, for instance, we're going to talk about quadratic forms and how that is helpful. So we'll focus on that next week. I just wanted to quickly check. Okay, let's continue on. Let's continue on. I want to do an example. After this example, I'm going to let you give you a little time to do some classwork. But let's take a matrix A here, and we're going to orthogonally diagonalize this matrix A, given that this matrix A has two eigenvalues. Okay, so let me give you a moment to copy this down. Let me know if you have any questions. Okay. How many eigenspaces are there for this symmetric matrix A? How many eigenspaces are there? Well, Eleni, okay, how many eigenvalues are there? Hold that thought. 2. So therefore, how many eigenspaces would there have to be? Just 2. That's right. Now if we had so this is a little bit different, right, than the first example you looked at. The first example we looked at, there were 3 distinct eigenvalues and 3 eigenspaces with the 3 eigenvectors, you know. Here we just have 2 eigenvalues and 2 eigenspaces. And what we're going to do is we're going to orthogonally diagonalize the matrix. Okay, and we're going to work it out by hand. So it's important that you take good notes on this. And when you do, I'm going to work it out by hand. You know the final exam, I'm going to ask you to work a problem like this, maybe even a couple of them out by hand, because it shows me that you understand the concepts. So, all right, so here we go. What's the first thing we have to find, class? What must we find? We're given the eigenvalues. That's nice. What do we need to find? So we want to write the matrix A as P times D times P transpose. How do we construct the matrix P? What must we find to construct this matrix P? We know the matrix D consists of the eigenvalues according to their multiplicities. Okay? But that's right. Very good, Ben. We have to find the eigenvectors, and we're going to have to normalize them too. But we're going to have to do a little more than that. So let's proceed. Okay, so again, just to summarize here, we want to find an orthogonal matrix P and a diagonal matrix D such that A equals P times D times P transpose. A is a symmetric matrix, so by theorem 2, there will exist such matrices P and D. Okay, so we're going to find the matrix P. To construct P, we have to find the eigenvectors. So first, we have to find a basis for the eigenspace corresponding to lambda 1 equals 7. So I set up the augmented matrix. And remember, class, when you have an augmented matrix, okay, when you're finding eigenvectors, you have to have a 0 vector included in your augmented matrix. Okay, sometimes, you know, on I think the last exam, a few of you might have lost a point or two because you didn't include that zero vector there. It needs to be there. Needs to be there, right? When you find an eigenvector, you are solving an augmented matrix. So, okay. We're going to work out the row operations. All right, and I don't think I think everything's pretty clear here, but just let me know if you have any questions. All we're doing is finding a basis for the eigenspace corresponding to lambda 1 equals 7. Which you've done many times. Let me know when you're ready to move to the next page. All right, are there any questions before we go to the next page? Are we ready? All right, very good. What do you notice about these two rows? Or those two equations? Are they different or the same? They're multiples of each other, so it's really the same equation. But I'll continue with the row operations. Okay, I'll continue with them, be very formal here. Okay, so what I'm going to do is I switch the first and second rows, and then I multiplied the first row by -2, added to the second row, and replaced the result in the second row. I mean, finally, I get the matrix in reduced echelon form. All right. We get our solution, and we write the solution in parametric vector form. Let me give you a little time to catch up here. Okay. All right. Any questions before we move forward? I sent one of you a quick chat message, by the way, just to let you know, not to distract you, just to wanted to make sure I got that out there. Okay. Okay. So thank you. Thank you. Excellent. Excellent. All right. So now we have a basis for an eigenspace. But of course, we're not going to use, this -1/2, 10. What can we replace that by? The 101's okay. That's a nice friendly eigenvector. What can we replace the -1/2, 10 by? What would you recommend? What's a better eigenvector than negative half, 1, 0? Here's what I'm trying to say. Hold on. Yeah, negative 1, 2, 0. Right. So in other words, you know, a basis for your eigenspace, you have negative 1 half, 1, 0, and 1, 0, 1. But the fraction here is hard to work with. So I'm going to replace negative 1 half, 1, 0 with the eigenvector negative 1, 2, 0. Multiply that eigenvector by 2. And so this is going to get me my eigenbasis for lambda 1 equals 7. Then what I have to do is find an eigenbasis for lambda 2 equals negative 2. Okay, so I'll give you a moment to copy this page down. So this is I'm working this example out for you because on the final exam, you'll have problems or like this. You know, it's going to be kind of a long problem. And it might be, who knows, it might be worth more than 10 points on the final exam. It might be worth 15 or 20 till I'm done, you know, till we're done. But the point is, you know, this problem, it's a problem that brings together a lot of the concepts that you learned. And so I'm trying to model good behavior by working it out. And I would want you to do the same on the final exam. So that's why I'm, you know, working it out. You were able to use MATLAB to get a lot of eigenvalues and eigenvectors on exam 4, and that's fine, that's good. But we don't want to forget the fundamentals, right? We don't want to forget the fundamentals. And okay, are we ready to move to the next page? Who's feeling good so far? Okay, good, Abby, good. Okay, all right, well, let's continue. So this is just standard, you know, standard stuff here. We're going to do some more row operations, and I don't know, I took a fair amount of row operations to get this matrix in reduced echelon form. Maybe you could do it in less, so I get it in reduced echelon form, And I then write my solution vector x in parametric vector form. So a basis for this eigenspace, okay, let me just, okay, so a basis for this eigenspace is just one vector, -1, -0.5, and 1. But of course, we could rewrite the basis as a nicer basis. And I'm wondering what a nicer eigenbasis would be. I mean, I know, but I'm just kind of asking you all. I agree, Catherine. I agree. Let's multiply the eigenvector by -2 to get a nicer eigenbasis. -2, -1, and 2. Okay, very good. I mean, look at all the stuff you've learned coming into play in this problem. All right. And we'll move to the next page when you're ready. I'm very happy that pretty much, I think, pretty much all of you are like you're here, and you're like really here. A colleague of mine said that his class, a person was like logged in, but the person was actually at Walmart during the class because he could hear him walking through Walmart. So I trust none of you are at Walmart during this time. So. All right, so we'll use this as our eigenbasis. And these are things you have to think about, when you're doing the math. You have to think about this kind of thing. Are there any questions at all before I go to the next page? All right, Natalie, very good. Natalie's good. Okay. All right, Benjamin's good. Okay, Abby, excellent. Okay, so here we are then. Here's the basis for the second eigenspace. And, you know, I'm going to construct the matrix P here with the eigenvectors I found and a matrix D. Okay. And it will turn out that the matrix A will equal P times D times P inverse. Okay, because these three eigenvectors are linearly independent. Okay. But the matrix A is not going to equal P times D times P transpose. And we'll ask why. So let me give you a moment to catch up here and think on that for a moment. Okay, so man, okay, we went to this effort, and sure enough, the matrix A. Oh, okay. So Benjamin's noticing something here, and some of you might notice it too. These vectors x1 and x2, for instance, are not orthogonal. They're not orthogonal, right? Now the vectors x1 and, well, let me just see one moment here. So, well, hold on. I want to ask you something here. So, is the vector x3 orthogonal to both the vectors x1 and x2? In other words, is the vector, let me write it the way I want to write it here. Is the vector x3 perpendicular to the vector x1? Yes or no? Hold on. Is the vector x3 perpendicular to x1? Somebody chat out the answer. Maybe we like hearing from everybody. Maybe somebody new, a new chat person. I mean, well, you know what I mean. Maybe somebody who hasn't chatted before. Don't worry, we don't bite in here. So what I'm asking is the vector x3 perpendicular to the vector x1? Are they orthogonal? This means orthogonal, this symbol, right? And while I'm at it too, I'll ask, is the vector x3 perpendicular to the vector x2? That's good, Haley. Yes, on both accounts. And we know that has to be true because the eigenvectors x1 and x2 come from one eigenspace, and the eigenvector x3 comes from another eigenspace, but the matrix A was symmetric. So vectors from different eigenspaces will be orthogonal to each other. So this is not a surprise. This is not a surprise. But look at the vectors from the first eigenspace consisting of eigenvectors x1 and x2. Okay, is the vector x1 perpendicular to the vector x2? Whoops. Are the eigenvectors x1 and x2 perpendicular? They're linearly independent. So x1 and x2 are in that first eigenspace, right? That first hold on. I might got this. Let me make sure I got this right here. Hold on. Yeah. The first eigenbasis consisted of vectors x1 and x2. x1 and x2 are linearly independent, clearly, but are they perpendicular, those vectors? All I need is a yes or a no. That's right, Benjamin, they're not. And so remember, the theorem about vectors being orthogonal applies to vectors in different eigenspaces. You can have vectors in the same eigenspace then that are not orthogonal. Even though the matrix A is symmetric, you can have vectors in the same eigenspace that are not orthogonal. But we understand that the matrix A ought to be able to be written as P times D times P transpose. So in order for that to happen, what do we have to do? What do we have to have? What kind of basis do we have to have for this what kind of basis do we need to have for, well, hold on. Let me go back here. Here was the basis for the eigenvalue corresponding to lambda 1 equals 7, consisted of x1 and x2, those eigenvectors. Now, is this an orthogonal basis? Is this an orthogonal basis here? It is not. That's right, Eleanor. Can we make it an orthogonal basis? Can we take the eigenspace corresponding to lambda 1 equals 7 and construct an orthogonal basis? We don't have an orthogonal basis now, but can we get one? Can we get an orthogonal basis for the eigenspace corresponding to lambda 1 equals 7? Yes, and that's right, Benjamin. We can use Graham-Schmidt. Oh my goodness, Graham-Schmidt's getting involved in this problem too. Okay, well, that's all right. That's all right. Okay, so let us continue here. So the reason why is that A is not equal to B times D times P transpose is X1 is not orthogonal. Hold on, let me write this. Why is this? It's because several reasons, but X1 is not currently, well, no, it's just not. It's not orthogonal to X2. Those two eigenvectors in that eigenbasis are not orthogonal. So what we're going to do is we're going to make them orthogonal. But also, what else do we need to do with our vectors in the matrix P? What else do we need to do in order to orthogonally diagonalize the matrix A? What do the lengths of the vectors in the matrix P have to be? The lengths are going to have to equal 1. That's right, Elaine. So I know that, I know that, the lecture might be going a little slow, but I'm just trying to make sure you're involved here. Even, I know that you're maybe not, well, I just want to make sure everybody's involved. So, all right, let's continue. So here I have summarized what we just discussed. Okay, and I'm going to let you copy this page down. We're almost there. After we get done with page 9, we'll get to the final page. But we need the columns of the matrix P to be orthonormal. Okay, and for the two eigenspaces, well, this is just a summary of what I just mentioned. So I'm going to let you copy all this down. And I might then repeat it, but let me give you a moment to copy this down. Okay, so, all right. We need to create an orthonormal basis for the span of the eigenvectors x1, x2. We'll use the Gram-Schmidt process. We'll let v1 equals x1, and then v2 will equal this vector. So now I know that incidentally for the, your work for the exam, don't forget to show, steps, right? All right, so everybody knows for exam 4, the work is due, officially due this Saturday at midnight. And the remedial problems, you have until 6:25 this Saturday to complete any remedial problems you need to do. Right, so you've been through this before. You know how this works. Please let me know if you have any questions. I naturally want to answer any questions you have. And let me know then when we can go to the next page. And to help me with Gram-Schmidt, I always like to have draw a little diagram. It just kind of reminds me how to do Gram-Schmidt. I got to find the projection of the vector x2 onto the subspace W. The subspace W is the space spanned by the eigenvector x1. So this here, of course, is the projection of the eigenvector x2 onto the subspace W, and we're going to subtract that projection vector from the vector x2, and that'll get us vector v2. How many find the little picture kind of helpful to remind them? I like using it, but how many of you kind of find the little picture to be just kind of nice to have, kind of ties in what you're doing here? Okay, good to hear, Benjamin. Okay. And like I said, for many of the problems, like on your exam, you had MATLAB to help you get eigenvectors and eigenvalues. But, we, of course, don't want to forget how to do that kind of thing. And so it's obviously a problem like this on a final exam. I realize it takes time to work through. And I'll recognize that in terms of the time, how many problems I assign and so forth. Okay, are we ready to move to the next page? Maybe give me a thumbs up. Okay, Abby, excellent, excellent. Let me just see one thing here. Where I said theorem 3 here, class, yeah, well, that theorem 3 is called the spectral theorem for symmetric matrices. And I'll show you that real quick. But let's go to the next page and finish this up. So the eigenvector V2 is going to be equal to -1/2, 2, and 1/2. And then I will make a better vector V2. All I need is a multiple of that. So I make V2 prime. That's -1, 4, and 1. So the set of vectors V1 and V2 prime is an orthogonal basis for the eigenspace corresponding to λ1 = 7. And so now all I have to do is normalize then my vectors in the matrix P. So let me just see those vectors. I kind of like to label the columns of that matrix P. I mean, isn't this the most beautiful stuff you've ever seen? I mean, this is really, really something here. So this is the eigenvector x. Well, no, hold on. Yeah, I just normalized my vectors. Okay. So V1, I normalized V1, I normalized V2 prime. Okay. And then the third eigenvector, which was -2, -1, and 2. Well, that if I normalize that eigenvector x3 has a length of 3, and so I just normalize it. And so this is the matrix P that's going to work. And this is the matrix D that's going to work. And really, this example, it really is sort of like everything we've done, like this example here is basically, I mean, a lot of the things you learned in chapters 1 through 6 got involved in this example. And it's just a great example. Think about how much you know today compared to how much you knew the first day when you took linear algebra, right? Back in, I guess, January, right? Just an incredible thing. What I did, of course, is this particular example that I went through is actually example 3 in the textbook. But of course, in the textbook, they leave out some details, and I filled in all the details for you. So you ought to be able to handle any problem that comes around. And I might mention also that for this problem, let me just see here, hold on. See if there's anything else I want to mention. I'll mention something here, but I want to make sure. Are there any questions? Any questions at all? Before we, I want to return to the book and try to finish this up here. Section 7.1 exercises, they're going to be due on Monday. So I'm going to make those available for you. And of course, you have section 6.6 due this Friday. All right, so who's feeling good? Maybe give me a thumbs up if you're feeling good. For this matrix P and this matrix D, A will equal P times D times P transpose. Thank you, Benjamin. Feeling good. Hung's good, excellent. Christopher's good. Wonderful. Okay, then let's move on. Let's move on here. So I want to go into the book real quick. Okay. And I want to just show you something relating to this actual example. So this example I worked out for you. Again, example 3, section 7.1. The book leaves out some details to save space. But one thing that I started off telling you the eigenvalues, but in example 3, they actually get the characteristic equation and then they factor it out, okay? And you can see 0, the characteristic equation, that 0 is going to equal negative the quantity lambda minus 7 squared times lambda plus 2. So this means that the eigenvalue 7 has multiplicity 2, and the eigenvalue of negative 2 has multiplicity 1. Well, remember the eigenspace corresponding to the eigenvalue lambda equals 7. That eigenspace was a 2-dimensional eigenspace, okay? And the eigenspace corresponding to lambda equals negative 2 was a 1-dimensional eigenspace. And that's no accident. That's no accident. That's another beautiful result, but it comes from the spectral theorem for symmetric matrices. Okay, the spectral theorem for symmetric matrices has the following properties. You know, of course, the matrix, if a square, an n by n matrix A, symmetric, has n real eigenvalues, counting multiplicities. Okay, but part B there, the dimension of each eigenspace equals the multiplicity of the root of the characteristic equation. Okay, so, and then part C you're aware of. Eigenspaces are mutually orthogonal. And then for D, the matrix A is orthogonally diagonalizable. Okay. So the only thing that, the last thing I'll mention here, because I want to give you some time in class to work. Last thing I'll mention is they talk about how you can take a matrix A and do what's called a spectral decomposition. A spectral decomposition. If you have a matrix A, a symmetric matrix A, and it equals P times D times P transpose, you can write that in terms of the expression in formula 2 there. the matrix A will equal lambda 1 times U1 transpose plus lambda 2 times U2 times U transpose. The U1 and U2 are orthonormal eigenvectors. Okay, and so you can write the matrix A in this very beautiful form, and that'll come up in your homework as well. Are there any questions before I stop the recording here? Okay, I'll stop the recording.